This is the first in a series of videos in which we'll be looking at past paper questions on magnetic force, electromagnetic force, and the motor. Now, in this first video, we'll be looking at a question from May June 2008, paper 2, question 6. Right? So this question is from May June 2008, paper 2, question 6. Now, I will apologize in advance for my drawing skills, or maybe I should say the lack thereof. For better diagrams, of course, you could always access the paper and look at the diagrams on the actual paper, right? Now, with that said, we'll proceed to the question, right? So this question basically starts off by showing us a diagram, which basically says, so it shows us this diagram here, which is listed at figure 6. So figure 6 shows a magnetic field between the poles of a strong magnet. So here we have the north pole of the magnet, and we have the south pole of the magnet, and of course we have the field lines which run from north to south, right? The first thing we're told to do is to complete the following diagrams to show, 1, the magnetic field due to a current carrying conductor where the current is directed into the plane of the paper. And this is a diagram given here for that part of the question. So part I of A wants us to basically complete this diagram to show the magnetic field due to a current carrying conductor where the current is directed into the plane of the paper. Now, to do this, we basically must apply Fleming's right-hand grip rule. Now, what exactly does Fleming's right-hand grip rule state? Now, according to Fleming's right-hand grip rule, if we imagine gripping a conductor in the palm of our right hand so that the thumb points in the direction of the current, that is conventional current, then the way in which the fingers curl around the conductor will give us the direction of the magnetic field lines, right? So once again, if we imagine gripping an electric conductor, a metallic conductor, in the palm of our right hands so that the thumb points in the direction of the current, then the way in which the fingers curl around the conductor will give us the direction of the magnetic field lines. And of course, we'll apply this to this particular question. Now, when it comes to currents, we basically have we have a convention for showing the current direction. And what is it? Now, we can have a current going into the board or into the paper, or out of the board or out of the paper. And we have particular ways of representing those. Now, in this particular case, we use an X to represent the current going into the board, and if the current is coming out of the board, we'd use a dot, right? In this particular question, the current is going into the board, right? So essentially, if you imagine a dot and you basically, or an arrow going away from you, then all you're basically seeing is the little X at the back, and that is why we basically use the X to represent the current is going into the board. If the dot or the arrow is basically coming towards you, then basically all you're seeing is the tip. And that is why we use a dot to represent the current that is coming out of the board. Right? So with that said, we'll basically apply Fleming's right-hand grip rule to put the direction or to show the direction of the magnetic field around this metallic conductor. Right? So once again, because the current is going into the board, our thumb, which represents the current direction, must be pointing into the board, right? Right? So the question had said the current is going into the plane of the paper as indicated by the X, and of course, using the board to represent the paper, then of course current must be going into the board. So you applying Fleming's right-hand grip rule, our thumb must be pointing into the board, and our fingers will curl like this. So in other words then, if this is our wire, we're just carrying a current into the board. Let's say this is our wire, carrying a current into the board. Our thumb will point into the board, and the thumb will curl down on this side and up on this side. And so therefore our field lines, which are a set of concentric circles, will look like this. Right? So in terms of the direction, once again, the field lines will curl down on this side, go around, and then go up on this side. So the field lines will go down and they will go up on this side. Right? Now, the next part of the question involves us we're asked to basically show the results when this wire is placed within this magnetic field. Now, because we're going to be looking at that, let's also put the field lines at the top here. So because they go down and up, at the top they will be going in this direction, and at the bottom they will be going in that direction. Right? That is very important for us to able to determine what is happening when this conductor is placed within this magnetic field, right? Now, let's go ahead and do that. Now, we have a uniform magnetic field between the north and the south poles of this magnet, and of course, the field lines are running from north to south as seen. We have a conductor which is basically carrying a current into the plane of the paper or into the board, and the field lines directions are shown as indicated. So above the wire, essentially the field lines are going to the right, and below the wire, the field lines are going to the left. So once again, we're going to be basically placing this this current carrying wire in this magnetic field, right? So once again, the field due to the magnets is going from north to south as a series of parallel lines, because the field of course is uniform, right? So if you look at the diagram, when you take this wire and you put it in this field, above the wire, the field lines due to this magnet and the field lines due to the wire will go in the same direction, right? So when you put the wire in the field above the magnet, remember that the field lines due to the conductor are, well, due to the magnet are going north to south. So above the wire, because these field lines are also going right to left, it means the field lines will go in the same direction above the wire. And remember that magnetic field strength basically is a vector quantity, which means that direction is important. So because the field lines are going the same direction, it means the magnetic field will get stronger above the wire, right? Now below the wire, as you can see, well, these field lines are still going from north to south, but for the wire, where the wire is concerned, the field lines are not, well, yeah, north to south. Where the wire is concerned, they are going in the opposite direction. And because these field lines are going in the opposite direction, what happens down here is that the magnetic field strength, of course, will cancel and the field will get weaker down here, right? So at the top, the field lines go in the same direction, right to left, and the field strength increases as the magnetic field gets stronger. Below the wire, the field lines go in opposite direction, which means that there is some cancellation taking place and the field gets weaker, and it therefore means that we'll have fewer field lines down here. Now in a diagram, we typically use the relative closeness of the magnetic field lines to indicate the strength of the magnetic field. So basically, if the field is very strong, we expect to see the field lines being very close, or we can say that we expect to see a large number of field lines in a particular space. However, if the field is weak, it means that we expect the field lines to be much further apart, or we can say that we expect to see only a few field lines in a particular space, and we'll basically try to show that on this diagram right here. So on the diagram, we'll still have some straight field lines, something like this, but near the wire they will kind of curve and something like that, right? So something like that. And of course, these field lines will be going in that direction, right? Below the wire, because the field lines are going in the opposite direction, there will have been some cancellation taking place, which basically means that there are not going to be many field lines down here. So we'll basically just draw a one field line to represent the field due to the magnets, right? And so essentially, this is what the field pattern looks like when the wire is placed between this between the magnets, right? 3 marks for that part of the question. So that was part A of the question, right? Now let's look at part B of the question and this lovely diagram, right? Now part B of the question says, figure 7 shows the end view of a simple DC motor, right? So what we have here is a DC motor. Now the DC motor basically comprises of, well, it has strong magnets. We can see the north and the south pole of the magnets. There is a coil of wire between the magnets, and the coil of wire, of course, is connected to this setup. Now the question goes on to ask, name the part labeled X. Now this part labeled X is what is called the commutator, or in some books you may see the split ring commutator. Right? So X is the commutator, or to be more specific, it's the split ring commutator, right? Now let's look at the other part as well, even though we weren't asked what they were. These rectangular looking things, these of course would be the carbon brushes. So this of course would be the carbon brushes, and they would basically make electrical contact between the external circuit and the split ring commutators, right? So this of course ABCD is a rectangular coil, and we can see that there are contacts from the coil leading to the split ring commutator, right? Of course we have the external circuit, and we have our cell, a group of cells of course is a battery, but because it's one we just call it a cell, and of course we have the switch in the circuit, right? So in the current setup we can see that the ends of the coil are making contact with the split ring commutator, right? Now what is going to happen here when the switch is closed? Let me look at the question to see exactly what they ask us. So they said tell us to name the part labeled X, and X of course is the split ring commutator, or just the commutator, all right? 1 mark for that. Now part 2 of the question asks or tells us explain what happens when the switch is closed. Your answer should include the direction of the current, the force acting, any rules applied, the direction of rotation, and how continuous rotation is achieved. So in our explanation we need to basically examine all of those things. So let me just jot down what we need to include. So we need to include the direction of the current, we also need to include the forces acting, also we need to include rules, any rules applied, and we also need to apply direction of rotation, and lastly we need to explain how continuous rotation is achieved. Right? So these are the things that we need to be able to explain. So let's start. Now, as the switch is open, then no current will be flowing, right? We expect that, right? However, when the switch is closed, we now have an external circuit, and we now have a path for the electric current to flow, and therefore the current flows. Now, we know that basically whenever we're dealing with electric circuit diagrams, we deal with what is called conventional current, and conventional current of course is the direction or flows in the direction that positive charge would flow. Now we know that basically when it comes to charges, the electrons are the mobile charge carriers, but of course we still show electric current to be flowing in the direction that positive charge would flow, and of course we call this current conventional current. So this would basically be the positive terminal of the battery, the long stroke, and this would be the negative. And therefore when our switch is closed, let me just modify the diagram to close the switch. When our switch is closed, it means that what we'll have is a conventional current I flowing in this direction around the circuit, right? So the current is of course flowing from the positive terminal of the battery, because we're talking about conventional current flow. Now the current flows through the battery. It goes through this carbon brush. Let's label these carbon brushes. Let's call this one P and this carbon brush Q. So the current goes through carbon brush P, enters the coil at this end and flows in this direction, right? So the current flows up this way, up DC, CB, and then down, and then of course exits the loop at carbon brush Q via this the end of the split ring commutator, right? So that is the direction of current, of course, when the switch is just closed, right? So we've basically deal with that part so far, right? Now let's talk about the forces acting, right? Now if we go back to this diagram over here a little bit before we get to this one, we know that basically whenever a current carrying conductor is placed in a magnetic field, it will experience a force, right? It will experience a force due to the magnetic fields interacting. So the magnetic fields interact, and this interaction basically creates a force which, if strong enough, will be made evident by the movement of the wire, right? Now the wire doesn't always move, but of course once the wire is carrying a current and there's a magnetic field around it, then it means that once you place that current carrying wire within a magnetic field, then there will be a force exerted on the wire, and of course there will be an equal and opposite force exerted on the magnets as well. The magnitude of this force will basically determine whether motion of the wire is visible or not, right? Now, this force, of course, can be predicted using what is called Fleming's left-hand rule. So in the previous part of the question, in order to show the field around this straight current carrying wire, we applied Fleming's right-hand grip rule. But in order to predict the direction of the force on this wire, we'll have to apply Fleming's left-hand rule. Now, we'll need it for that diagram as well. So before we actually go any further with this, let's talk about Fleming's left-hand rule. Now, according to Fleming's left-hand rule, if you basically place the first and the second finger of your left hand at right angles so that they point in the direction of the magnetic field and conventional current respectively, then the direction in which the thumb points will be the direction of the thrust or the force on the conductor. So once again, if you place the first and second finger of your right hand your left hand rather, at right angles to each other so that they point in the direction of the magnetic field and the direction of conventional current, then the direction in which the thumb points will be in the direction of the thrust or the force on the wire. So typically, Fleming's left-hand rule is used to predict the direction of the force on the current carrying conductor, right? So one thing we must note is that, right? So I will say certain things and I will stress certain sounds, right? The first finger represents a magnetic field. And in the case of the magnetic field, we're talking about the field that the wire finds itself in. So in the case of this particular question, because this wire is placed within this magnetic field between the north and the south pole, if we're predicting the direction of the force on this wire, the first finger must point in the direction of this field, which of course is from north to south, right? So once again, the first finger represents the direction of the magnetic field lines. Good? The second finger represents the direction of conventional current. The second finger represents the direction of conventional current. And by conventional current, we're talking about the direction that positive charge would flow. So what this means that basically is if we have positive charges moving in a certain direction, then the second finger will be going in that direction. If, however, we're talking about the movement of electrons, whichever direction electrons flow in, then conventional current will basically flow in the opposite direction, and the second finger must therefore go in the opposite direction to that in which electrons are flowing. Good? So the second finger points in the direction of the conventional current, and this current, of course, will be the current which is being carried by the wire. Good? So once you place the first finger in the direction of the magnetic field lines and the second finger in the direction of the conventional current, the direction in which the thumb points will give us the direction of the thrust, which is of course synonym for force on the wire, right? Now, some books may use the word motion instead to say that the thumb points in the direction of the motion. But the fact of the matter is, there isn't always motion because the forces may not be strong enough for the wire to actually move. However, even if the force is very, very weak, there will still be a force once there is a current in the wire and the wire is placed in a magnetic field. So for that reason, I use the word thrust to signify the thumb, and of course the word thrust is a synonym for force. Good? Now, having said that, let's now try and predict the direction of the force on this wire placed in this magnetic field. So once again, our first finger is going to point in the direction of the magnetic field. Now let's imagine that these magnets are basically placed flat against this board, and therefore it means that the field lines are going from north to south. Good? So this finger points in that direction. Now the current, or the conventional current, as evidenced by the X, is going into the board. So we must now rotate our hand so that this second finger points into the board. So we come like this, rotate our hand, and therefore the middle finger or the second finger is now going into the board, and our first finger, of course, is pointing north to south in the direction of the field. With that done, it leaves our thumb pointing towards the ground, and therefore this means that this will be the direction of the force on this current carrying conductor. So therefore this conductor will experience a force in this direction. Right? So that is the direction of the force on this conductor as predicted using Fleming's left-hand rule. Now, having done that, let's go back to our question here, because we'll have to use it to predict the direction of the force on the sides of this coil. Good? So we saw that basically when the circuit is closed, then the current flows, the conventional current flows on the positive terminal of the battery, this direction through carbon brush P, through the one end of the split ring commutator, through this end, the coil D, C, B, A, and so on. Right? Now let's use Fleming's left-hand rule to predict the direction of the force on each of these sides of the coil, in particular sides DC and sides AB. Now, the coil is clearly within the magnetic field produced by these magnets. So therefore, we're going to have our magnetic field lines, of course, going from north to south, right? So the magnetic field lines are going from north to south. All right, so those are magnetic field lines going from north to south. Good. Now, let's apply Fleming's left-hand rule to side DC of the coil. Now again, according to Fleming's left-hand rule, the first finger must point in the direction of the magnetic field. The second finger must point in the direction of the conventional current, and that will leave the thumb pointing in the direction of the thrust or the force on the conductor. So, the field is going from north to south, like this, right? Field is going from north to south. The current is going in that direction. So the field north to south. Let me just try to rotate my hand. Field north to south. Current is going in that direction, right, like that. And essentially, that leaves the thumb, right? So north to south. Let me drop my hand a little bit lower so it makes more sense. So the field is going north to south, right? And yeah, and the current is going up like that. So this basically leaves the thumb pointing downwards, and this basically means that there's a downward force on this side of the coil. Right, so let's go again. So the field is going north to south like this, right? The current is going that way, and this leaves a force pointing downwards, not vertically downwards, but I mean, downwards on that side of the coil, right? Something like that. Good? Yeah, like that. Right. Now we must also do the same thing on this end of the coil. Now, this end of the coil, the field is still going in the same direction. The field lines haven't changed. However, this time the current is going in the opposite direction. So let's predict that now. So the field is still going from north to south, but this time, of course, as we can see, the current is coming down like this, and essentially this thumb is pointing kind of out. Yeah, kind of out, or we cannot say up. You understand? So something like that. So the diagram because the diagram wasn't drawn the best, it's kind of hard to actually get the correct directions of these forces. If we're using the paper, then it would definitely better, right? Because on the diagram, right, so on the diagram, paper, it's a much better diagram. It's a much better diagram on the paper, right? So basically what's supposed to happen is that these forces are supposed to be going in opposite directions. So because this one is a downward force essentially, then this one is going to be an upward force, kind of like this. Right? So field, current, right? So right, so yeah. Alright, and then down here it would be field, current, yeah. Right, so basically what this shows is that these two forces are going to be going essentially in opposite directions. Now, the forces are going to be of equal magnitude because the current in each side of the coil will be the same. And there's going to be a perpendicular distance between these two forces, right? These two forces are going to be essentially perpendicular. So essentially we have equal and opposite perpendicular forces, and we call that a couple, right? In physics we call that a couple, and there's going to be a torque or a turning effect due to this couple. So based on these directions, this side of the coil will be pushed down, this side will be pushed up, and therefore the coil will rotate this way. So this will cause a rotation like that, and this will cause a rotation like that. So therefore, essentially, the coil will be rotating in a clockwise direction, right? So the coil will be rotated in a clockwise direction. So as I said on the paper, the diagram is drawn much better, which allows for better manipulation of the left hand. And so on side CD, right, there's going to be a downward force, right? So on side CD, there's going to be a downward force, and on side AB, there's going to be an upward force. So these forces are equal in magnitude, but in opposite direction, and therefore provide a couple, or act as a couple, and basically produce a torque or turning effect. And this essentially causes the coil to rotate in a clockwise direction. So in this diagram, due to this current flowing this way, the coil basically rotates in a clockwise direction. So we talk about the direction of the current, the forces acting. We talk about the rules applied, which of course is Fleming's left-hand rule. And of course, the direction of rotation would be clockwise. Good? Now, we have one more thing to look at. That is how continuous rotation is achieved. So once again, if you're looking at this question, just look at if you're watching this video, just look at the question on the paper, as the diagram is is drawn much better. Now, when we just start out, these ends of the coil are connected to the ends of the split ring. They're in contact with the split ring, and that allows the current to actually flow through the carbon brushes, through the split ring, around the coil, and out like this. However, as you can see from these two forces, the coil is going to be rotating. And let's say it was initially horizontal. After rotating, say, through 90 degrees, yes, so the 90 degrees, the end of the coil will now be aligned with these spaces. And therefore, what happens is that the circuit will no longer be complete because the coil is not connected or is not touching the split ring. So after a 90-degree rotation, the ends of the coil would be perfectly aligned with the spaces. The connection is broken, and therefore no current flows in the coil momentarily. But what happens to the coil? Does the coil stop? No. The coil doesn't stop because its momentum will keep it flowing in that direction. So its momentum will keep it flowing, or keep it rotating rather, keep it moving, until it once again becomes in contact with the carbon brushes, right? So as I said before, after rotating through 90 degrees, the coil will be, and these two ends will be aligned with these spaces. There's no longer connection to the circuit, no current flows, and however, the coil doesn't stop because its momentum will keep it rotating. So it then comes back into contact with the carbon brushes. This end would basically be over here, this end over here, right? After it has rotated through 90 degrees, essentially what will happen is this. We label these sides DC, AB. If it has rotated, not 90 degrees, but rather 180 degrees, so half a revolution. After it has rotated through 180 degrees, essentially, these ends become interchanged. So D basically goes over here, C basically goes over there, over here becomes A, over there becomes B, right? So this basically becomes DC, and this becomes AB, if we're keeping the letters, right? But of course, what this will show is that regardless of where we label AB or CD, the current is still flowing in this direction on this side of the coil. And therefore, the force on it is still going to be acting down, right? The current will still be flowing up in this direction, and therefore the force will still be acting up. And therefore, as a result, there is still going to be a clockwise rotation. And this is basically what allows the coil to rotate in the same direction continuously. So continuous rotation is achieved due to the fact that the direction of the current around the coil does not change. And when we say the direction of the current around the coil, we're not talking about, say, for instance, A, B, C, D, but in terms of around the coil, right? So in terms of the current flowing around the coil, there's always going to be a, anti-clockwise flowing of the current around this coil, and this results in a clockwise rotation of the coil. Right? So in this question, we're able to look at Fleming's right-hand grip rule applied to the current in a current carrying conductor and show the magnetic field lines around the current carrying conductor. We're also able to apply Fleming's left-hand rule to predict the direction of the force on a conductor which is placed in a magnetic field, and of course we're able to use it to explain the rotation of a coil in a DC motor.